Now we're going to talk about algebraic data structures from his very own Buck Shlegeris.
So, good afternoon, ladies and gentlemen. Today I'm going to be talking about basically a magic trick that you can do with data structures. And like the first time I was shown this trick, I thought it was just madness. And occasionally I present it to people basically as a magic trick. You know, I'd kind of like you to treat me as if I was, a traveling magician who ended up at the wrong conference and, had to, rapidly improvise something to do with computer science that was still, enough like a magic trick. So first, before I can do this, I need to explain a bit of Haskell-style data structures. Problem is, a bunch of you are already new people, so you know this stuff already. So I would like some brave members of the audience to try and think about some problems which, at the moment, they don't look like they have anything to do with data structures, but you'll see. So some questions, that you could work on. If anyone's got a piece of paper and a pen, I would appreciate their efforts on this. How many binary trees of size 5 are there? So for instance, that's a binary tree of size 5, where that line looks a bit more like that. So, presumably there's some number of those. I think it'd be fun for you to try and figure it out, and then the idea is later I'll, remove all your thunder by showing the simple way that you can differentiate an expression 5 times and just get it correctly. But anyway, so introduction to Haskell data structures for those who either didn't pay attention in 1100 or aren't from ANU. So, that's an interesting order. So the kind of thing we have in Haskell is a data structure that looks something like this. So, like an example application of this, we might have the item Buck, who is a student with the name Buck Shlegeris, which is a string, and the student number 5192430, which is an int, and the expected value to the university of $25 or whatever. So this is similar to things you might be used to from other languages. So for instance, if you're used to C, you might be used to seeing, a struct with, a string there and the int for the uni ID and the float for a dollar value. And, we'd write something like this, if this is indeed how you correctly see. Ooh, I think that's semicolon. God. Or even more roughly, if you don't mind approximation, it's a bit like this in Python, but in Python there's no actual type restrictions. Like, if you wanted to have it, with the name being 53, Python would just be like, sure, it's a thing, that's a pointer. I was trying to explain this to someone in my Python shoot the other day, and they were saying, sorry, you can't have a list of arbitrary elements? Like, why not? Like, how does it know? But so for the Java students among you, it's also roughly equivalent to public class student, 40 lines of awful cruft, basically with the constructor method that takes a string, an integer, and a double, and assigns those to fields in your object. So we've got all these different ways of referring to this basic concept of my object has these 3 things about it. And in a mathematical context, it's also very similar to this kind of thing here, where we say a student is an element of the Cartesian product of a string, an integer, and a real number. Who knows that this is an integer? Who knows that this is a real number? Good, because, just to get an idea of my audience. So basically what this is saying is, anything which has a string, an integer, and a real number, it's basically something that could be an element of type student. Because when we're talking about types, we might as well be talking about sets, because the question, is this thing of the correct type, and does this type check, can be phrased as, is this thing here an element of our set, student or whatever. So this is actually a very close similarity, which we get in math to Haskell, because Haskell was invented by mathematicians who like highly abstract concepts and whatever. So those things that we saw there, where we have some, student, and a student has a string, an int, and a float, we call these product types. Who knows why that would be called a product type? Any guesses? There's one.
Sets are Cartesian.
Yeah, because it's a Cartesian product of sets. A Cartesian product, incidentally, for those of you who don't know, and how good am I at guessing audience responses, is something like this, the Cartesian product of 0, 1, and 2, and A, B, and C is, 0 and A, 0 and B, 0 and C, 1 and A, 1 and B, 1 and C. Or, so it's the set of things which have one element from each of these sets. So that's one answer. Can anyone else think of a connection between products and the kind of stuff we're doing here? What's a product mean in everyday life? It means multiplication. And, one thing that, I'm slightly foreshadowing here if there are only 2 different integers and 3 different strings, and there's only 1 real number, then there's only going to be 6 different things that you can have as a student. Because, the number of things in the Cartesian product of 2 sets is just going to be the product of the sizes of the 2 sets. Foreshadow, it's okay if you don't get it right now. So if we've got a product type, the other thing in mathematics is a sum type. Just a quick aside here. The way I phrase it is kind of, we've got a thing that looks like a product type, why don't we make a sum type? And that's not actually that different to how people actually do math. They say, this thing looks like multiplication, addition is a thing too, maybe we can try to do addition too. And just to get into the mathematical spirit of this talk, it's pretty accurate to try and, we have this thing that does products, maybe we have something that does sums as well, and you just try and make one of those up. So let's imagine that, let's try and stretch our imaginations to imagine that the ANU cares largely about us students for our dollar value to the university. But UNSW it's far more, charitable with its intentions. So, a UNSW student has just a string for their name and an int for their uni ID because, the UNSW doesn't worry so much about the dollar value of a student to it. So we could say that a student is an ANU student with a string, an int, and a float, or a UNSW student with a string and an int. So our new type we call this a sum type, because it's either this thing there or that thing there. And they're not that obvious a concept if you don't come from a language which has that kind of thing in them. They're kind of like a union type in C. Most of you are Java programmers, right? Of those of you who aren't Haskell programmers. So I actually found someone who's found a way of doing this in Java using abstract classes. Where basically, for instance, we want our binary trees to have nodes which are also trees. So if we have some abstract class tree, and we say that every node has 2 children which are trees, and then we use branches and leaves as an implementation of our abstract class trees, that is an incredibly ugly and awful way to represent the same kind of idea that we've got here in Haskell in Java. I trust you'll be able to believe me that the Java equivalent is ugly and massive and awful. Thanks very much to this blog for going to the effort of writing all that. So, some question you might have is, what about polymorphism / generics? It'd be nice if we could have a way of using, if we've got a data structure list of integer and another for list of string, it would be nice to reuse our code, considering, our functions, length of string or map or filter or any of these are basically the same thing. And it would be nice to have polymorphism, or as you call it in Java, generics. So in Haskell, you can have data structures with type variables. So a really common one that I think is a really cool thing that people who don't know Haskell should be aware of is the maybe type. So for instance, an instantation of this would be maybe int. So a maybe int is either just an int or it's nothing. And the reason that's really nice is because often you want to be able to represent a computation which either works or fails in some obvious way. And this really represents that, because if we're doing some function which sometimes works over the integers, such as division, we might want it to, if it works, return an integer and otherwise return nothing. So if we were doing this in Python, we'd have it raise an exception if it didn't happen, or return none. But that causes all kinds of awful things like automatically checking if things are none, but the test actually comes true if they're equal to 0 as well. So this is a really nice thing. Another thing we have in Haskell is either A, B. Now this one hasn't actually come up in 1100, so this is actually new. So either A, B is either something left A or right B. So for instance, if we have our actual type, a really common one is to represent an error using this. So if your computation comes out right, as in correct, because Haskell programmers love bad puns, then you return right B. So for instance, say you've got some computation which will either work and return you a float, or fail and return you an error message. You'll have either string, float. And if it works, you might get something of the type, right 16.0. And if it doesn't work, you get something of the type, left, division by 0 or whatever. So this is all making sense so far. I trust you'll be able to, do the Comp 1100 first assignment in Haskell using all this stuff. So far we have product types and sum types, and the big next step is recursion. So it would be nice if we could refer to our own data types, in their own definition. And we get things like this. So a list of integers is the empty list, or it's a list with an integer and a list of integers. So who here, everyone who does 1100 should immediately understand why that works. Everyone else, it might take a little bit of thinking, but basically, the empty list is a list, and a list is basically something on the front of any other list. And we can construct it by saying, list 5 empty list. This must be a list because it fits that second rule. And now that we know that that's a list, then we know that this is also a list because it follows that rule. It so happens that we have syntactic sugar, so we can actually write that down as the list of 3 and 5. But this is one way of implementing it behind the scenes. And one of the things I particularly love about Haskell is that you actually do this, and you actually can do this, whereas in Python, if you implemented everything directly, it'd just be god-awful and ugly. And I only really understood the actual semantics of Python after really looking them up, whereas in Haskell, you get hit with them right in the face. Or alternatively, we could do this polymorphically. A list of things of type A is either the empty list, or it's a list with a thing of type A and a list of things of type A. Cool. So this gives us superpowers. We can basically define whatever the hell we want using this kind of stuff. A binary tree, for instance, is going to be null, or a node with a thing and 2 binary trees. You'll remember the binary tree I drew earlier had, everything in the binary tree. This is my A, and this is a binary tree down here. And so on. So we can all agree, binary trees can basically be described by that kind of rule. We're all cool with this? I'm kind of, awkwardly trying to crash teach, what takes a few weeks of lectures in 1100 in a few minutes to a bunch of people, some of whom already know this stuff already. Anyway, so here's just one final example of the kind of stuff we can do with this. A file system item is either a file which has a file object, or it's a folder which has a string for its name, and then a list of file system items. For instance, this might represent a folder which has some folders inside it and also some files inside it. So, this stuff actually works fairly nicely for representing that kind of stuff. Anyway, on to the cool part of this presentation, which the intro is now prepared you for. So, combinatorics with data structures. So, all of this kind of stuff here, we can actually ask questions about how many things are of a particular type. And it turns out that there's some really, really beautiful structure and isomorphisms there. So imagine that the conference dinner has, 3 options for your main course. We've got, you can have ramen, or you can have miso soup, or you can have the Ichiban Delicious. And for your drink, we also have the option of Mother or Mountain Dew. I just picked the most computer science stereotypes I could think of. I apologize very much. So how many different options for dinner do we have here? If we've got 3 main course things and 2 drinks. 6. Very good. How do we get 6? 2 times 3. Fantastic. We can do basic math. You are qualified to get a computer science degree at ANU. So we can write down our data structure. Dinner is dinner with a food and a drink. So the number of things we have, this is a product type, we remember, right? And the number of things we can have for dinner is the product of the number of things we have as a food and the number of things we have as a drink. So this is all whoa, product types. They're like products in mathematics, even though they're products in computer science. Imagine that instead the CompCon committee had budget constraints owing to things like, having to suddenly buy everyone pizza for yesterday's lunch or whatever. And now you get a food or a drink. So how many different things do we have for dinner now? 5. Very good. Why?
Sum.
It's the sum, yeah. Because you either get food or a drink. So if there's 8 different things you can have for food, and there's 3 different things you can have for a drink, that's 8 plus 3 is 11 things you can have for dinner. So we agree that the number of things in a sum type is the sum of the things in each of its little types. So let's try this with lists. And this is the bit where you should start being confused, because I was very confused the first time this was shown to me. We've got a list equals the empty list, list of type A, is the empty list, or it's a list which has a thing of type A and a list of A's. So this bar here saying it could be this or this, that's basically a plus, right? We all agree that's basically a plus because it's or, and or is basically plus. Let's rewrite that as a plus. Empty list is one thing, it's only going to be one thing. Let's rewrite that as 1. We don't need this. If we've got A and a list of A, we have this and that. What operation is that? Product type times. So we have a list of A equals 1 plus A times list of A. That seems entirely legitimate to everyone, right? Nothing sketchy is going on. So imagine, like, that's not very nice because it's recursive and, like, no one likes recursion, right? So why don't we factorize? Because that seems totally legit. So we subtract a times list of a from both sides. You know, minus a equals 1. Now let's divide both sides by list of a. And madness and madness and madness, and also I'm really bad at algebra. And we get list of a equals 1 over 1 minus a. So you might have seen this, you know, we've got... And that actually makes no sense at all, right? Like, to start with, to do this kind of math, we have to assume that A, you know, it can't be 1, among other things, because if A were 1, then we'd have division by 0, and in math you aren't generally allowed to divide by whatever you want. So it actually kind of makes sense. So does anyone recognize this from anywhere? This number, it's geometric series. What's a geometric series? Yeah. So this equals 1 plus a squared plus a cubed plus a to the 4, and so on. Does this make any sense to anyone? Because a list, it's 0 things, or it's 1 thing, or it's 2 things, or it's 3 things, or it's 4 things. So is that kind of making sense to people? So the infinite, like, a list of A is basically an infinite sum of different sized tuples of A. Where, you know, if there's 1 thing in my list, it's A, and if there's 4 things in my list, it's A to the 4. So we want the infinite sum of those, and so we've got 1 and 1 minus A. Now there's some niggling little constraints here, like the fact that this identity only holds when A is strictly between 0 and 1, and we notice that A is the size of a set, so it's probably not going to be strictly between 0 and 1. But if we just kind of close our eyes and cross our fingers, you'll find that it all works out, I think. So basically what we've just discovered is data types have what's called generating functions. And the famous book on generating functions is literally called Generating Functionology by Herbert S. Wolf. And if you look at the back cover, what do you call them? The recommendation is, from some other guy, Herbert S. Wolf is a true black belt generating functionologist. Just a really good book. I suppose, if you discover lots of math, I suppose you can call it whatever you want. So basically what this means is the coefficient of x to the n tells you how many data structures there are with n things of type x. So in this case, there is exactly one kind of list with 3 elements of a in it, right? Because the only list is, like that, right? There's not multiple different ways of doing it. Whereas, remember at the beginning when I said, binary trees, how many are there of type 5, with 5 elements in them? There is going to be some coefficient in front of there, and it's probably not going to be 1. And so in that case, we'd expect our power series, when we solve for what our tree is, and then we write it out as a power series, we expect it, a tree. How many trees are there of size 0? 1, yeah. How many trees are there of size 1? 1, yep. Size 2? 2? Yeah. 2a squared and so on. So it'd be really nice if we could automatically do that algebraically. So now it's time to do so, right? We go Python data structures.py. This is the most awful piece of code. Is it really called that? Generating functions. So this is the most awful piece of code I've written in my life because half of it is in Haskell and half of it is in Python. So I've got a list of examples of Haskell data structures here. So what are we expecting maybe A to correspond to? Because it's going to be some kind of function. So if there are A things, in my type, now we look at the maybe type, we're expecting 1 more, right? That seems sensible. So maybe corresponds to, the function which adds 1 to something. Does that make sense to people? Is everyone cool with that? Cool, I've got a bunch of nods from the audience, that's always good. So we look at my function which automatically does it, and indeed, the solution to maybe is a plus 1, where a was our variable. Let's look at the next one. We've got a list, which is the empty list, or append list A. Automatic calculation, and indeed it works. So we get our solution to what a list is of type A is -1 and a -1. And here's our power series expansion of this, where a power series expansion is where you approximate a function as a polynomial to clarify for the non-mathy people. So, our list is 1 plus a squared plus a cubed plus a to the 4, and so on. So nothing interesting there so far. I don't suppose anyone actually tried to figure out how many binary trees there are of size 5. But if so, I beat you to it. There's 42. And we just literally got this by using the quadratic formula, which is why I didn't do it by hand. On the formula, a tree is the empty tree, or it's an element and then 2 trees, and you solve that for t, and then you differentiate it a bunch of times to get your power series expansion, and you get there's 42 of them with 5 elements. What do we have next? Okay, I've called this next one Behaviour. And can anyone guess how many there's going to be of various sizes? So another way of writing Behaviour is data Behaviour of A. It's a list of tuples of A and maybe A. So can anyone guess what the pattern of the number of different ways we can have, n things in this data structure is going to be? I'll give you a clue. It's in the name. What's that?
It's in the name.
Yeah. So what is it going to be?
The Fibonacci.
Now, why is this going to be the Fibonacci sequence? Like, you're completely correct. If we go to my terminal and press enter, yeah, we get this expression here, which has the power series expansion. Everyone knows what the Fibonacci sequence is, right? We get this power series expansion, 1, 1, 2, 3, 5, 8, 13, 21. I'd recognize that anywhere. Does anyone have any idea why that's true? It's because if I've got this as my data structure.
No, because it's the golden ratio you get when you go 1 plus x squared plus x. You're solving that.
That is true. I'm not counting that as an answer because it's still a mystery to me why that's the golden ratio. But you're correct. That is the golden ratio is the solution to that equation. The way I'd explain it is, if we want to know how many different ways there are of having a Fibonacci, type with 8 elements, it's going to be A and maybe A can be 2 elements of A or 1 element of A, right? Because the second thing can be just A or it can be nothing. So this is going to either be 2 elements of A or 1 element of A. And so the number of ways of having it with 8 elements is the number of ways of having it with 6 elements, because then you have 2 elements of A, or the number of ways of having it with 7 elements, because then you get 1 element of A. So we have, Behaviour of A equals Behaviour of A minus 2 plus Behaviour of A minus 1. And there we go, Fibonacci sequence. These get successively less sensible and sane from here. What do we have? A bool list of A, which is a long list of either a Boolean or an A, which is an alternating series. This is where it stops being sensible and just starts becoming weird. Apparently there's -1 data structures like that, which have 2 elements of type A in them. It just gets a bit crazy from there. Oh no, this one's kind of fun. We can agree that, if you've got a double 2 is obvious. If we've got a tuple of A's and bools, if we've got 5 elements of A, then we also add 5 bools, where a bool is a Boolean. And there's 2 different Booleans, and we can just pick any of those, so there's going to be 32. So, this is just the, the power series where, for A to the cube, there's also going to be 8 ways of doing it, because you've also got a Boolean in there. The last one in there I've just got because it's funny and amuses me. It's 0. So allegedly there are 0 ways of having this, even though as far as I can tell it's entirely legitimate to have something that might just be a list. It's because this comes out to be -1. And when you have -1 times list plus list, -1 times x plus x is 0. So apparently it's 0. So it'd be really nice if I knew what the hell this meant. When these are sensible, we know what they mean. With a list, the coefficients tell us how many different ways there are of doing it with a tree. But then you've got stuff like that, or, if I put another A in here, who knows what'll happen. Occasionally I get fractions and crazy stuff that makes no sense at all. But I'm going to leave that as an open question because it's confusing and hard. And the only explanation is in French. This guy wrote a paper on combinatorial species, André Joyal or something, and it's in French, and there aren't any translations of it, and I have no idea how much of this stuff is in there with a really good explanation. But I can't read it because I don't speak French. My father was always really upset I chose not to study French in school, and this is the first time I've had real sympathy for his position. Anyway, so some results from this. Imagine that I wanted to have a data structure which only has examples with a prime number of items. So, I can't have, if it's that data structure of ints, I can't have 1, 2, 3, 4, because that's not prime. And the answer is basically I can prove some things about context-free grammars that say that the only restrictions on sizes I can have in my data structures are unions of congruency classes. Anyone know what a congruency class is? Basically, it just means the only rules is to there is a data structure with n elements if n mod m is in, some list, 0, 3, and 6 for some n. So, for instance, I can have it so that 6n plus 3 and 6n plus 2, all of those have representatives, nothing else does. So, for instance, one sad thing about that is, imagine if I wanted to define a data type of matrices. So, it's a list of lists where all of the lists inside have the same number of elements. That's entirely impossible. You have to write a function that checks that your matrices actually, we don't want to have it, 0, 1, and the next row is 0, 1, 3, next one's, 0, 3. Because it's not a real matrix because they aren't matched up. And it turns out there's no way inside the Haskell type system of enforcing this. So the question I have on this at the moment is how do I classify the functions which you can generate by a Haskell data structure? So for instance, we've seen we can get the constant 1, we can get the Fibonacci sequence, we can get exponentials. I have no idea in general what the values are. Anyway, it's time for the crazy bit of this talk. And this is the bit which was first shown to me and had to be explained to me a few times. So first we're going to explain what the zipper is. So the zipper of a data type is the type corresponding to one whole context. So for instance, if my type is a tuple of 3 elements, 3 elements of A, the zipper over this corresponds to the type corresponding to all the ways that I can choose one of these A's and scribble it out. I could have done that, or I could have done, this. So the kind of results I get, if it was ints, I could have 2 scribble mark 3, or I could have 1, 3 scribble mark and all these. So we want the data type which corresponds to these. So there's a bunch of ways to do it. For instance, for this one here, we could just represent 3 tuples and have an integer. And the integer tells you which one is scribbled out. However, that's fairly unsatisfying because we can't use our type system to confirm that it's actually what it's doing. We could have the tuple 1 and then the number 53,000 because the type system doesn't have any idea what the numbers are doing. So we want another type that corresponds to those. So can anyone see what the zipper over a tuple of 3 elements is? So we want a data structure which corresponds to all the ways that we can be somewhere in this. Does anyone see it? Yeah. It's going to be basically, data 3-zip equals left AA or right, right AA or middle AA. Where if it's left AA, that means the whole is on the left, and then we have 2 actual things of type A. If it's right AA, it means the whole is on the right, and then we have 2 actual things of type A. And if it's middle AA, we mean the whole is in the middle, and then we have 2 things of type AA. This here is, this one's A squared, and this one's A squared, and this is a plus, and this is an A squared. So we might as well, simplify the expression and turn it into just 3 times A squared, which we do by having some enumeration type with 3 elements, and a tuple of those and 2 A's. So we have this here, a tuple of 3 elements of type A. Can anyone remind me what expression this is equivalent to? Yep, this is A cubed. So we have A cubed, when we take the zipper, it goes to 3A squared. Now, does anyone know what the zipper over a list is going to be? We want to represent, if we've got this list here, 1, 2, blah, blah, blah. Does anyone know how we can represent exactly a whole in this list? Yes.
It's 2 lists.
It is 2 lists because we want to have one list to represent the things before the whole and one list to represent the things after the whole. If we just did it by having our one list and then a number, that would work some of the time, But again, there's no type system constraint on what the number can be, so the number could be -3 or 57,000, and there would be no actual type system constraint guaranteeing that our zipper is correct. So why would we use zippers? It happens in Haskell. They actually make things a lot faster, and again, we have type system constraints. So, I'll come back to that later. So we've got the derivative of a pair. A pair is a squared, right? We all agree? What is the zipper over a pair? It's either going to be left A or right A, which corresponds to 2A. So we have a squared goes to 2A. We have a cubed goes to 3a squared. Is anyone noticing a pattern? Does this look like something from an entirely unrelated branch of mathematics, which assumes we have continuous objects and, uncountable sets and all this stuff? That's right, guys. It's differentiation. And why would it be differentiation, I ask you? Does that make intuitive sense to anyone? It certainly didn't make intuitive sense to me until I actually figured out for myself why I think it makes sense. But it sort of makes sense. Differentiation is a linear operator, as in if we go, k, like k f of x, and we differentiate that, we get k times the derivative of f of x. If we've got some random information off on the side and we've got a data structure and we differentiate it, we kind of expect to have the random information off the side and then the derivative of the data structure. We can verify all the rules on differentiation. That still doesn't intuitively describe to me why differentiating this thing here, to clarify, if you differentiate this, you do get 1 on 1 minus a squared, which is indeed 2 lists. So this now means that we've discovered this ridiculous isomorphism between data structures and zippers, and then algebraic expressions of some kind which occasionally make sense, and they're zippers. And I think that's pretty cool. So let's look at a few of the superpowers we have with this. At the beginning of this talk, I wondered if anyone could tell me a function which was equivalent to this sum here. X plus 2x squared plus 3x cubed, and so on. And I don't think there's any way that most people know of doing this. So one way of doing this, and when I was writing my slides, I was thinking, so I need a data structure that corresponds to, there's one way of having it with 1 element, or 2 ways of having it with 2 elements, or 3 ways of having it with 3 elements. And it turns out to be 2 lists. Because, if you have 2 lists and you have to have 5 elements, then you can have the first list end after the first, or the second, or the third, or the fourth, or the fifth element. And so you end up with 6 actually, but -1, and you should be right. So we can now generate arbitrary power series with this kind of thing. And this is the example of how you do that one. So here's the combinatorics problem for you. Does anyone have any idea off the top of their head how you'd find the number of ways in which one can distribute 4 identical objects into 5 ordered boxes with at most 1 object in each of the first 3 boxes and at most 2 in the last 2 boxes? No intuitive ideas? So I can just do, we have at most 1 object in each of the first 3 boxes. So if we have at most 1 object in the first 3 boxes, then that's either 0 objects or 1 object in the first 3 boxes. And then we have 0, 1, or 2 in the last 2 boxes, which is 1 plus x squared in the last 2, which gives us this thing here, which I'm not expecting should, ooh, dearie me. I'm not expecting that should make intuitive sense. I don't trust IPython at all. But if we expand this, I don't trust this software. It's like Mathematica, but free software. Yeah, so we get this here, and we wanted the number of ways. So this is basically talking about the data structure which has those constraints on it. And now we want to know the number of ways of storing, how many was it? 4 identical objects. So we look at the coefficient of x to the 4, And there are exactly 18 ways of doing this. So I think that's pretty cool. So here's one of the really cool bits of it. Like this was my favorite. So what's the obvious question when we find out that there's differentiation? What was that?
What is integration?
What's integration? Yeah, so the answer of what's integration is, you're trying to find the type whose zipper is this, and the answer is you can do it, but it's really ugly. Good question. What's another question we want to ask?
Can I do sin x?
Can I do sin x? That's a really cool question. So who knows the power series expansion of sin x? It's this god-awful thing with fractions in front of it. And we don't quite know how to do fractions, because as far as we know, these coefficients, in all the cases which we've understood it, are just how many different ways there are of of having this data structure. So if we've got binary trees, there's multiple ways of doing it, and so we've got a positive number in the coefficient. So we want to have fractions to get sin x, so we aren't quite sure how to do that yet. The question which first popped into my head is differentiation e to the x. E to the x is its own derivative. I want to find a type which is its own derivative. And so who knows what e to the x is as a power series? Go.
1 plus x plus 1 over 2 factorial plus x over 3.
Yep, and so on. So that's why we're doing this next bit, because we want to find a data structure that corresponds to that. So
that'll give you sin over it. That'll give you sin x as well, because it'll be the even one.
Yeah, if you put a complex number in there. So if we don't care about a distinction between various things, we often talk about identifying them. So when we define the rational numbers in mathematics, we often say, 2 on 4 and 1 on 2 are the same thing, because we identify things if, the ratio between them is the same. So, for example, an unordered pair might be half a squared, because for every pair, we can write it 2 ways, and if we don't care about the order, then we don't care, which way we wrote it. So there's only half of the ways we'd normally have, which would be a squared, so we get half a squared. And of course, the derivative of this is a, which makes sense, because if we don't care where the whole is, then to describe a whole in an unordered pair, we just need to describe one of the elements, and obviously the whole is in the other place, and no one cares which place it is. Or, an unordered triple would be a sixth of a cubed. Does anyone get where I'm going with that? The unordered constraint seems to turn x to the 4, for instance, into x to the 4 on 4 factorial, because there's 4 factorial different ways of ordering things. So an unordered list, also known as a multiset. So a multiset is, it's either 0 things or it's one thing, and there's obviously only one way of ordering one thing. How many ways are there of ordering 2 things? 2. How many ways are there of ordering 3 things? Yep. How many ways are there of ordering 4 things? 4 factorial, and so on. And this is E, and, that basically shows us that a multiset, where a multiset is defined as a list which does not mind order, basically that's the same thing as e to the x. And of course this makes sense, because what's the zipper over a multiset? If we don't care, again, where somewhere is in a multiset, then it's just going to be another multiset, because to describe removing something from our multiset, we just have a new multiset, which is everything that's left. So that's entirely as expected. So here is the crux of my talk, and also pretty much the end of my talk, and what I think is the only thing that I actually figured out originally in this field. So why does a zipper correspond to the derivative anyway? Does anyone have any ideas why the zipper corresponds to the derivative? We can kind of see some reasons why it should, which is, differentiation is a linear operator, and we can see why it should work on tuples. But I think the way to think of it is a combinatorics problem. So, as I write here, the zipper with 6 elements has to have 1 element for every shape of the original data structure, which has 7 elements. So, the coefficient of x to the 6 is going to be the coefficient of x to the 7 times 7. And if we make some dodgy mathematical behavior and assume that we can describe every other data structure as the infinite sum of different sized tuples with different coefficients, I think that kind of makes sense. On a really quick side, who knows what a context-free grammar is? Cool. Context-free grammars are these things in theory of computation and also Comp 1140, which basically describe languages really well. I think it would be fantastic. The first thing I saw when I saw this was we have a way of saying whether there is, particular things in some particular language And until last night, I had this, really exciting dream of maybe I can find some algebraic way of describing whether something is in a context-free grammar based only on some algebraic fact. And then I, started talking with a PhD student, and we did math for 2 hours, and I realized that I'd have to have an uncountably infinite dimensional vector space and some stupid operators and stuff that made no sense. So I got really sad. But basically, it turns out that if we use my magic, one question in context-free grammars is we want to know if a grammar is unambiguous, as in, you know how English is ambiguous? If I say a dog and a cat and buck, I could be saying dog and cat and buck, or I could be saying dog and cat and buck. It would be nice to know if that kind of thing was not present in a particular language. We can use this kind of work to get a sufficient but not necessary condition for a grammar to be unambiguous. We can also sadly get a necessary but not sufficient condition for a string to be in a grammar. And there's a sad face there because I was really hoping to have cool results here. But it turns out that you can't actually do this stuff very sensibly because you get awful things like uncountable infinities. Anyway, that's pretty much the end of my talk. If you're interested in all this stuff, as you very well should be, the advised reading is, of course, Generating Functionology. I've got a few well-advised blog posts on it. This is John Baez. Anyone heard of John Baez? John Baez is a really cool math guy who basically, he has this blog where he talks about cool things in math. It's very good. Conor McBride was the guy who was on a train station, in a train station when he realized, wait a second, zippers is just differentiation. And he wrote the paper that started this all off. So thank you very much. I hope that you found it interesting and entertaining.